Welcome to this explainer, brought to you by Forge College. Today, we're tackling handling complex Solana transactions. Now, if you've been working through our Programming with Solana track, specifically the module on interacting with clients and programs, you already know we've been deep in the weeds of client interactions. Well, today we're taking a massive leap forward. We're moving into full-blown orchestration. We're taking all those scattered pieces, those individual instructions, and assembling them into a beautiful, highly complex machine that actually runs without crashing your devnet builds.
You see, building the perfect machine on Solana requires getting every single sequence exactly right. You don't just conjure up a massive complex transaction out of nowhere. No, you build it up by mastering the simple systems first. Because honestly, just one misstep, like a flipped instruction order or a forgotten signature, and your beautifully crafted transaction just grinds to a halt. It's exactly like building a Swiss watch. Every single gear matters.
Think back to our previous lesson, Client Library Optimization Techniques. In that one, you polished the individual cogs. We're talking things like connection pooling and reducing latency. That was all micro-optimization, which is great, but a bucket full of perfectly polished cogs doesn't actually get you anywhere, right? So today, we shift gears to orchestration. We're zooming way out to build the entire engine.
Here is our master blueprint for today. We'll start by moving from optimization to orchestration. Then we'll structure your blueprint, figure out who pays the fees, dive into the art of partial signing, run through simulation and safety checks, and finally, wrap up the build. Let's get right into it.
Starting with Section 1, moving from optimization to orchestration and transitioning into complex, end-to-end multi-instruction flows.
When you actually transition to stuffing multiple instructions into a single transaction, you are no longer just dealing with the quirks of one isolated program. You're dealing with the cumulative effect of several of them. All your previous architectural choices are heavily magnified here, and that introduces a whole host of new operational failure modes. Suddenly, you're forced to manage some serious trade-offs, like how do these instructions compose sequentially? Or how in the world do you handle partial signing across multiple different keypairs? You also have to guarantee atomicity, make sure you aren't blowing up your compute budget, and, oh yeah, deal with those super fun transient RPC failures.
Which brings us to Section 2, structuring your transaction blueprint and establishing that sequential timeline of execution. Here's the deal with Solana. The runtime executes instructions strictly sequentially. That means your transaction is a timeline, not just a random bag of concurrent tasks. Your order literally dictates your success. Think of this strict assembly line kind of like fueling a machine. You absolutely must attach your compute budget fuel tank in step 1, way before you try executing any heavy program logic in steps 2 or 3. If you wait until the heavy lifting starts to suddenly ask for more compute units, the runtime is just going to instantly fail your transaction. So, fuel up first, then lift. Moving on to Section 3, who pays the fees? This is all about assigning economic responsibility to minimize friction.
Every single transaction costs compute fees, right? So someone has to step up and be the designated generous friend covering the tab for this whole mechanical operation. Now, you might have signer A and signer B authorizing actions on their own specific accounts, but you can actually assign a completely separate role, the fee payer. And why would you do this? Well, imagine your transaction fails just because of a random network blip. If you're using a dedicated, well-funded back-end fee payer account, your system can automatically retry that transaction smoothly in the background. You don't have to constantly ping your original end users asking for more gas money. It is an absolutely massive UX upgrade for sure.
All right, Section 4, the art of partial signing and procuring those authorizations without exposing everyone at once. In the real world, your multiple signers aren't all sitting shoulder to shoulder at the exact same computer at the exact same millisecond. That is where partial signing saves the day. You can really think of it just like passing a digital birthday card around the office. You serialize the transaction, you have your local fee payer sign it, and then you pass that partially signed object over the network. Remote users can then add their signatures one by one. The transaction itself isn't fully valid until everybody signs, but the beauty is they don't have to do it all at the exact same time.
Now, you might be wondering, but wait, won't the transaction's block hash expire while we're sitting around gathering all these signatures? That is a fantastic question, and the answer is a resounding yes. This is literally the ticking time bomb of partial signing. Every single transaction requires a recent block hash to prevent replay attacks, and that hash is only valid for a couple of minutes. So you absolutely cannot leave that digital birthday card sitting on Bob's desk over the weekend. You must collect those partial signatures quickly, or you're going to be starting the whole process over from scratch.
Let's jump into Section 5, Simulation and Safety Checks. Time to run this transaction through the testing facility. Look, you wouldn't build a highly complex, multi-part engine and then just turn the key without testing it first, right? That's just asking for trouble. This simulation step is your absolute best friend. It catches deterministic runtime and compute errors before you actually spend any real fees. By running Simulate Transaction, you're basically asking the Solana cluster to pretend to run your code against the current blockchain state. Did you mess up the instruction order? Did you forget a compute hint? The simulation is going to tell you, and it does it entirely for free.
So what does a successfully assembled machine actually look like post-simulation? First off, your simulation returns a null error. That is your green light right there. Then, when you send it, you'll get a valid base 58 signature string back. But hold on, don't celebrate quite yet. You absolutely must poll using confirmed transaction until you see that confirmed status. And the ultimate victory lap? That's verifying on devnet that your expected state changes actually happened. Did those LAMP ports actually move? If the answer is yes, then congratulations, you've succeeded.
Finally, Section 6, wrapping up the build, orchestrating that final submission, and handling failures.
Okay, so we have optimized, we've structured, we've gathered signatures, and we've simulated. Now let's walk through the timeline that represents your entire end-to-end orchestration flow. This is the final blueprint for your codebase, so definitely memorize the sequence. Step 1. Compose your instructions in sequential order. Step 2. Fetch a fresh block hash. Step 3. Partially sign with your local keys. Step 4. Run that simulation. Step 5. Collect the final remote signatures. And Step 6. Send it to the network and wait for confirmation. That's the whole shebang.
But let's be real for a second. Hiccups are completely inevitable. A gear's gonna slip at some point. If you hit a rate limit error, don't just sit there and hammer the RPC. Use exponential backoff retries. What if you get a block hash not found error? Well, that just means you took way too long gathering those signatures, so fetch a fresh one and re-sign. Compute limits exceeded? You just need a bigger fuel tank, so add budget hints or split up the transaction. And for those terrifying partial state failures, where instruction A works but B completely fails, you're going to have to rely on robust, custom client-side compensation logic to clean up the mess.
So I want to leave you with a thought. How are you going to implement structured error handling for your next transaction build? As you ponder that for our next lesson, remember to head over to forge.college to learn more about this subject and tons of other amazing Web3 topics. Building complex Solana transactions is definitely a challenge, but by moving from isolated tweaks to strategic orchestration, you really can build incredible systems. Thank you so much for joining this explainer made by Forge College, and I'll see you in the next one.